One. All right. Hey, everyone. Welcome back here to stage number one of SAE International's Battery Manufacturing Simulation Summit 2026. We've already had half a dozen sessions. We've got half a dozen more after this. We are right in the middle, the sweet spot of the event. And we're really excited to see that we have folks from at least, I think it was like kind of 11 different time zones logged in. That's why we like to get together online, is kind of shrink the world a little bit and sometimes reduce travel. Quick reminder that this session, as well as all the previous sessions and the remaining sessions, will be recorded. It'll appear there in about 15 to 30 minutes after this wraps up in the replay area, and you can revisit all the content there for the next year. Again, also, I want to give shout outs to ComSol for being our gold sponsor, to Element for being our silver, and to Mopac and CPEG for being our bronze sponsors. Because of their support, their generosity, you all paid exactly nothing to attend this event. No pesky expense reports to fill out, and that's worth its weight in gold. However, speaking of traveling and pesky expense reports, we're really excited to have Dania here. She's co-founder and VP of Technology at Qnovo. She is actually coming to us from the road. She's coming to an office or from a hotel in Detroit, where she was there for Autotech. She was a finalist for their Women Automotive Leader Award. So congratulations on the great nomination. We're hoping that the Wi-Fi holds up in the hotel. But Dania, I'm sorry to say you probably are going to have expense reports to fill out when you get back. So hopefully you don't mind. All right. So thanks for being here. Our virtual stage is yours. Next 25 minutes, half hour is yours. You can share with the group a little bit about how battery optimization makes battery reuse possible. Thanks for being here. The stage is yours.
Okay, thank you. Good afternoon or morning, everyone. I'm really happy to be here today. And I'm excited to talk about software and the role of adding battery intelligence, especially when it comes to second life batteries. Being able to manage a battery and monitor that battery from cradle to grave really enables it to be healthy throughout its life. And that enables that to have a second life, and who knows, maybe even potentially a third life. Okay, all right, I'm good. So think about your phone. When you know your phone at about maybe year 2 or 3, depending on how you use it, it starts to slow down. It doesn't last as long as it normally does. And you'll notice that because you have to charge it more often, but it still works. And for the most part, you can probably still use it for another year, maybe 2, depending on how you use your phone. And now if you scale that up to an EV battery pack, which is 75 to 100 kilowatt hours, when you think about that EV battery pack, the automotive industry says when it reaches that state, it's at the end of its life. But that's not really true, because it just means it's at the end of its first life, because it can no longer meet the really constrained demands of the EV in terms of the power required for acceleration and for fast charging. So even though it can't meet the power that's required for an EV, it can still power a house, or it can still be used for grid applications. So all it needs is a little checkup to be able to see what is the state of that battery. And so you can decide, well, what would be the kind of the subsequent application that it can be used at. And today, there are many retired EV packs that are just sitting in warehouses. And because nobody can confidently tear them apart and grade them to see if they can be used for second life or not. So as a result, they just sit there and they're waiting. And so today I want to focus the presentation on that gap in terms of what do you do when a pack is retired, and how do you commission it to go into second life. When we think about second life batteries, I mean, today there are second life applications from used EVs, and these can be battery packs that were in an EV that maybe was in an accident and can no longer be used and still has plenty of capacity that's left. But how do you really know that the cells in that battery pack are okay? How do you know that there aren't any latent defects in that battery pack? So if you think about it from a second life perspective, we don't fully understand all the degradation mechanisms that are there to be able to assess the health of a second life battery. We know in first life, we know the aging mechanisms that take place in first life. We know the models that are associated with identifying degradation in a first life. But when it comes to the second life, actually the battery is just chemically different. You have additional chemicals that byproducts from some of the degradation and the environment that that battery pack had been exposed to. And those chemically change the reactions that are taking place in that cell. And so when you look at it, it becomes hard to determine if those degradation mechanisms are going to have additional impact. And today we look at traditional methods, we look at capacity, or we look at, a cycle count, or we look at an odometer reading that will tell you some way that this is what the state of the battery is. But if you look at capacity, for example, and you look at cells and they have the same capacity, it doesn't mean their health is exactly the same. It means that they can change over time. Most cells today, I would say like 80-90% of the cells are degrade predictively based on methods that are predictive. But there's that small percentage of cells that are more prone to accelerated aging, and that accelerated aging could be because of the presence of lithium plating. It could be because just manufacturing variations. It could be just the use case, the way the cells were used. So when you try to compare these cells together, it becomes very difficult to determine if they have the same health, even though maybe, for example, their capacities are the same. And that's why you need a different way to be able to address what is the true health of these cells before before you can use them for second life, because as we know in lithium-ion batteries, aging is very nonlinear. So when we look at these different degradation mechanisms that create that non-uniform aging, they all independently and collectively make the cells age faster. And I'm not going to go through all of them, but I will touch on operating conditions and specifically temperature. When you look at a battery pack, typically the cells in the middle of the pack tend to be hotter than the cells that are on the outside. And they tend to be anywhere between 5 to 10 degrees hotter than what you see in the corner cells. So that means that over time, these are exposed to a different thermal profile compared to the other cells. So you take that battery pack and now you charge it 1,000 times, and then you put it in different geographical locations, put it, in the desert in Arizona, or you put it in Alaska where it's cold. And now it comes time to assess and if you can reuse these types of battery packs. And when you take them apart and you have to assess the cells, if you just measure capacity, the capacity of the cell in the middle compared to the cell on the outside could be exactly the same. But because of the thermal gradients, they're going to degrade in a different way. So maybe the cell in the middle can be closer to a knee compared to the cells on the outside that can still last for another, 5 or 10 years. So it becomes important to be able to identify how to manage or how to assess what the health of these cells will be. Another form of degradation also that we see is pinholes in a separator, which surprisingly are pretty prevalent in electric vehicle batteries. A pinhole is essentially just a hole in that separator. And what happens over time is it creates a short circuit, which can lead to a thermal runaway. And in the beginning, all pinholes are benign. In fact, most defects are benign in the beginning, and it's only through use and aging that these defects can materialize and create more side reactions that then leads to a safety event. Today, BMS will detect the pinhole if there's a presence of a pinhole or something is wrong at a point where it can no longer balance the series elements, and it detects a higher leakage current. And that's where it can be detected by the BMS. So from the time you start using it until that point, there's really nothing that the BMS can see. Meanwhile, this is brewing in the background. So if you think of it, the BMS is almost like a smoke alarm, that the smoke alarm goes off right when there's a fire, compared to if you have a diagnostic scan, it's going to tell you if anything else is brewing before it actually turns into something. And so that is the key that is required in order to understand what happens, what are some of the degradation modes that are associated with these defects that are showing up that you cannot measure with traditional measurements like capacity, resistance, or just looking what the BMS can do here. So let me step back a little bit and tell you what we do and how we do it at Qnovo. So Qnovo, we are a battery software intelligence data company, where we treat batteries. We don't treat them as just passive components. We actually treat them as very dynamic intelligent systems. And what we use the adaptive and predictive algorithms to really make batteries smarter. And I'll dive into that in a little while. And we've been doing this for the past 16 years, really putting a lot of the intelligence around how batteries should work, and specifically how batteries should work when they're out into the real world. Because a lot of times, a lot of the focus is what happens in a lab and how you can optimize around lab conditions, which are very controlled. And then when you put it out into the real world, it doesn't work because it's in a very uncontrolled environment. So how do we make sure these batteries are working under real world changing conditions and adapt to those conditions to minimize degradation and maintain the battery health? So what we've done is there are really two key innovations around this. The first one is putting the methodology in software around using EIS to be able to measure some of the chemical processes that are taking place in real time. And the second one, which is a critical one, is a closed loop optimization to manage degradation. And closed loop is essential when we talk about batteries because no two batteries are alike. Even when you make millions of them every day, there are still differences. I mean, think of it like twins. Twins may be identical, but they still have differences, and it's the same with batteries. And these differences under certain conditions really just become exacerbated and can lead to, undesirable performance, or they can lead to an unfortunate safety event. So today, the way batteries are charged, they're charged statically, maybe using a lookup table that will change based on temperature, but doesn't really change much beyond that. And it's very static. So you charge the battery the same way each and every time, which leads to more degradation. You start to see more varying performance because the cells it's not really looking inside the cell to see how it's changing. What we do is we stimulate the battery with the charging current and measure its response, and then interpret what that response means. So behind those measurements are models that interpret these measurements to be able to determine how the battery is aging. Is it aging because there's the presence of lithium plating, or is it excessive SCI growth, or is it high temperature exposure? So all of that is built into the models. And then the models they're not assessing how the battery is today, but they're also looking forward. So they're predictive. So what would happen to the battery 6 months from now if it's exposed to these conditions? And then we go through and we do a closed loop optimization, meaning closing the loop on the charging, modifying the charging to minimize degradation in the cell. And of course, not every cell performs the same way, so you minimize it based on the degradation of how that particular cell is feeling. And because we do this during every charge cycle, so we have a historical profile of how the battery is aging, then we know if there's a defect or something is going wrong in the battery, we already have the early signals because we're measuring because we have these fingerprints and these responses that are being measured really in real time. So we'll know ahead of time that something is brewing before it actually turns into something bad. And our algorithm runs independently on every series element in a battery pack. So that means each series element has its own historical profile, and you'll be able to see how it's evolving and changing. So you'll know where the weak cells are in the algorithm, and the algorithm will make sure to tailor to that weak cell and bring its performance up to the same as the other cells. And so this becomes really essential in terms of really managing, especially large packs or small packs into the real world. Today, our solution has shipped in over 200 million cell phones, and now we are in EVs. So let me show you an example of a real world condition with using our software. So this is a pretty harsh test. It's a real world test, harsh test in a vehicle that you have two vehicles, one with step charging, which is the standard static charging, and one that has the Qnovo software. And what you see here is because we are controlling the cell and we're managing it, you actually get half the damage that you see with standard charging. And the reason for that is because we're mitigating the degradation in real time under the very changing environmental conditions. And this is really under very cold weather, multiple fast charging cycles per day, and over a stretch of about 3 or 4 months. So the damage that's incurred was quite a bit, as you can see on the step charging, but with adaptive charging, you can minimize that. And that is the power of software, and that is the power of having adaptive charging. You have to adapt to the environment around you, and then you have to listen to what's going on inside the cell to be able to adapt the charging as the cell is kind of feeling at that point. Now, when we look at some of the requirements for Second Life application, everybody, if you look at across the ecosystem, everybody agrees. You look at OEMs, you look at insurers, you look at recyclers, everybody agrees on these 5 requirements. The first 4 are pretty well understood. Yes, you have to have accuracy in your SOH, and your SOH has to be an electrochemical fingerprint. Of course, it cannot just be like a capacity value. And then you have to have parameters, these what you call diagnostic parameters that are tied to these electrochemical properties so that you know how to sort cells. So for example, if cells have been exposed to lithium plating, they should be under one bin compared to cells that have not been exposed to it. And they have to be predictive. So you can't look at just today. For example, if a cell is at 85% capacity, is it going to hit a knee tomorrow, or is it going to hit a knee 12 years from now? It has to be predictive, has to look forward. And you would need to understand what is the fault with these cells. So some of them can be recycled and some cannot. So you have to be able to diagnose that. But the one that really breaks everything is the scalability. Scaling the testing is a big, big deal in deploying Second Life batteries, because today you can achieve accuracy in a lab. You can have fancy equipment. You can have, 2 days to a week to assess the cells, but it doesn't scale. If you have a facility that's processing 10,000 packs a year, which is tens of millions of cells, how do you do that so you have it in real time? Because every cell needs to have its own battery kind of cell passport that tells you about its electrochemical history and what its prognostics are. So you have to have that for every single cell. And if your method of scaling is going to cost you more than what the residual value of the cell is, then it's already a non-starter. So that doesn't work. So you have to have something that's cheap and fast and can make that assessment in real time to be able to process that and to be able to enable the use of Second Life. So the way we do it, especially from our health and safety diagnostics, the software that we have, is we go beyond the traditional methods, and that is by really understanding what's happening inside the cells. So we take the signals or the input from the BMS, the current, the voltage, temperature, SOC, time, and we run it through our models. And our models then generate a set of metrics, somewhere between 10 to 15, depending on the use case, depending on the type of cell. And these metrics, what they do is they isolate normal aging from abnormal aging. Normal aging is aging as expected, your typical SEI growth. And abnormal aging is it's aging because of lithium plating, or it's aging because you have a pinhole, or aging based on some other reasons. And based on those, then you can get an assessment in terms of where the cells fall between your normal aging, which we call life metrics, and your abnormal aging, which we call health metrics. And from that, we can rank the cell in order of least healthy to most healthy. We typically rank them on a scale of 100 to a 0, where 100 means healthy and 0 means unhealthy. And that way, because the algorithm runs really on every series element, you will have that ranking and the score for that cell all the time. So you can do this every single cycle, and you can look at it. Or if you're doing this assessment, you can get you can understand exactly where the weak cells are, or where the least unhealthy cells are. And this becomes important for sorting, because if cells cannot be reused, then they would go directly to then they would not be used for Second Life applications. And our software has been, obviously, we've integrated into vehicles and other applications. But what's important is when it's right on the edge, sitting right next to the battery, so you can monitor at any time. And it can flag anytime there's something wrong, because you're right there next to the battery. We also have it as a cloud service as well, so that, for fleet applications, when you have connectivity, you can get the data into the cloud, and then it'll do the analysis also of the different battery packs in the cloud as well. So they're two different methods of doing that. And so by being able to monitor the battery, and by being able to manage the degradation through its first life, you really help it age gracefully. And if it's not doing well from the beginning, you kind of help it grow old even more gracefully. And so that helps in terms of classifying the cells in terms of healthy and unhealthy. So even within a pack, there will be some cells that are still in pretty good shape that can be used for higher end applications, and other ones that are in okay shape that can be used for medium end applications, and the ones that are completely unhealthy that should not be used anywhere. And so by being able to manage it, then you can enhance and enable that sorting and binning period to be just much more efficient. And when it comes to energy storage, then you can manage new and used cells together within the same kind of the same framework, because you'll know exactly what the health of these cells are before they go into it. So you already have the kind of the battery passport for these before they before they go into the Second Life application. So the bottom line is really software is an enabler. Software is completely necessary for Second Life. And in fact, software is really necessary for batteries, because the more and more batteries that are going to be deployed, you can't leave them on their own. They actually need to be accompanied by software in order to keep them healthy in their first life and then take them into their second life. And that's it. Thank you.
No, thank you so much. That is really exactly what we're looking for, and very insightful. I think the rankings piece is interesting to me. I one of my favorite online accounts is We Rank Dogs, and so as we talk about ranking, let's talk about batteries here. um, that was the best ranking segue I could think of. All right, so I, I'm horrified. Can you elaborate a little bit on how some predictive indicators can rank and bin cells so that a mixed system of new and aged cells can be managed confidently without compromising longevity or performance?
Yeah, understanding, first of all, understanding what is happening with the cell. So you need to be able to diagnose exactly what's going on in the cell. And once you diagnose it, for example, if a cell already is starting to show signs of lithium plating, then from a prediction standpoint, you know it's not going to last you too long because this is going to only evolve over time. So the predictive indicators are really necessary to be able to see not just today, what happens 6 months from now? What happens a year from now? Is the cell more prone to faster degradation than other cells, for example? And so those are the early indicators that we look at. And then when you're binning cells, then you can bin the healthier ones to go in certain applications and the kind of unhealthier ones to just be put to the side and completely retired.
Sure. All right. And so let's talk about the EVs again for a second. So obviously now EVs are kind of coming back into the sort of public consciousness the last couple of months. So can you explain a little bit again, going back to one of your earlier slides, about why a battery that may no longer be an ideal fit for an EV is still pretty valuable in terms of grid storage?
Yeah, absolutely. So for EV, the requirements are very strict in terms of power requirements, energy requirements. And then once you cannot meet them, then that's it. The battery has to be retired. And an EV environment is very harsh compared to an energy storage environment. You've got fast charging, you've got high C rates, you've got temperature gradients, high power that's going through that battery. So it's going to degrade in a different way. You look at energy storage, I mean, energy storage is just stationary for the most part, right? So your degradation that's going to take place is different. Your C rates are very low. And then the temperature is more controlled, but your degradation and energy storage is more calendar aging that's going to take place because it's stationary most of the time. And then every once in a while it wakes up. So it's a very different environment. So because the EV environment is so strict, once you're just deviate away from these really tight requirements, then you need to retire it because, you can't have, if your range becomes less or you can't fast charge it anymore, then, then it's no good for that reason. And that's how you go to energy storage.
Sure. Yeah, I feel if my sedentary lifestyle, if I was a battery, I would be more suited for grid storage versus being put into an EV. All right, final question. How do you see the business development opportunities needing to be evolved to get a battery from retirement to energy storage stations?
Yeah, that's a great question. I mean, I think it's a whole ecosystem that has to work together because you've got there has to be this is all still new, right? How do you take these retired packs and then who is going to be or who will be responsible for taking them apart and classifying them and seeing if they have to if they can be reused. So you have to work between the OEMs, maybe the battery vendors, the insurers, the integrators, energy storage. So it has to be like a full ecosystem that has to work together in order to bring this and make it viable. I don't think it's a one entity thing. So it's a lot about partnerships to be able to bring this to life.
All right, great. Thank you so much for giving us half an hour of your time.
Yeah.
Thank you, Dear Hotels Wi-Fi, for holding up and doing the job. But most importantly, again, congratulations on being named a Women Automotive Leader at Autotech. It's a wonderful nomination, so I hope you are very proud. It's very, very well earned, very well deserved.
Thank you so much.
You're welcome. All right, so everyone, that wraps up this session. As a reminder, this will be recorded. It'll appear over there in the left side navigation replay area in about 15, 20 minutes or so. Otherwise, you can now head over to stage number 2 for the session about exploring design trade-offs through molecular or modular modeling. That's going to be underway in about 60 seconds over on stage 2. So head on over there, check out the networking area. Dania, thanks so much. Have a wonderful, safe trip back to California.
Thank you so much.
Great.
Bye.